Dear students, now we are well aware of the circuit of a tuned collector oscillator, and we further proceed towards its mathematical analysis. And for the mathematical analysis, we need to know the H parameter equivalent circuit of this tuned collector oscillator. So we will just refresh what our H parameters are. So we know that if we focus on like a common emitter configuration of a transistor, it is very clear that this emitter, it is a part of input circuit as well as it's part of output circuit. It means any fluctuations or changes at the output side, they are fed to or they affect the parameters at the input side. Similarly, any fluctuations or changes along the input side are fed through this common emitter terminal towards the output side, and the effect of output towards the input and input towards the output, these are basically given by the H parameters of this circuit. From where these H parameters come out, that we know that for the input side there are two basic parameters. One is the voltage. For the common emitter configuration, this voltage will be VB, and current IB. Again, there are two output parameters, and for the common emitter it is VC and IC. Now from these four parameters, we take two as independent and two other as dependent, and from other mathematical equations we get these factors, that my VB is equal to HIE IB plus HRE VC, IC is equal to HFE IB plus HOE VC. Now again, just a glimpse of physical significance of all these things. We have done this topic in very detail previously, but I want to just refresh your minds what it was. So this is VB. It means it is to do with the voltage only. And HIE, it gives the input impedance of the total circuit. So when input impedance and the current flowing through it are multiplied, we get the factor I into R, that is the voltage. Then the second factor, HREVC. Here my HRE, it is defined as the open circuit reverse voltage ratio. Open circuit reverse voltage ratio. The name is very conveying. Open circuit. Open circuit means that you make the currents of input circuit 0. That I make IB equal to 0 by detaching the battery from here. Then the voltages of the output circuit will be affecting the input circuit, and it will provide me with a equivalent voltage source along the input side. That is, in very simple words, even when the current in the input circuit is 0, then the voltages from the output circuit are going to affect the input circuit, and this effect is carried by this factor, which is a voltage source HREVC. Then the second equation is IC. IC is HFEIB. This HFEIB, this is called the forward current ratio with the output short circuit. That even if I short circuit this output circuit, but still the current factors from the input circuit will be affecting my output circuit, and this total effect is clubbed in these two terms, HFE and IB. And the last term, HOEVC. This HOE, this is the admittance, that is the reverse of resistance, that is VC divided by resistance. Again it gives me a current factor. So this total equation, it is giving me this circuit, which is totally equivalent to voltage. And this circuit, this is giving me a total circuit which is in the form of the current sources and the current only. So this is the H parameter analysis of a common emitter configuration. Now this circuit will be further extended for this tuned collector oscillator. So you can very well see that this HIE is simply cut paste over here, HREVC is simply cut paste, HFE, IB, HOE. That this is the H parameter equivalent circuit for the transistor only. And what are the other factors? The effect of these two resistances is put into a single term RB. Okay, and then is this tank circuit C and L, and any resistances in this L, it is that is shown by this resistance whose value will be equal to R. And this LC tuned circuit is magnetically coupled with this L1. So another secondary coil L1 over here. So this is the total circuit in terms of H parameters for a tuned collector oscillator. And I hope that you understand it. The further mathematical steps, I will be solving the article from the modern electronics book as per your syllabi. So I will be directly doing it from the book to avoid any confusions in it, so that when you open your book you are directly able to understand what is written over here. So we start from here. You can very well see that this L, that is inductor, and this resistance R, they are in series with each other, and further they are in parallel to this capacitor C. And if we take Z as their equivalent impedance, okay, so this combination, that is R plus iota omega L, where what is iota omega L? This is the inductive reactance of this inductor. R and iota omega L, they are in series, and 1 by iota omega C, this is the capacitive reactance of this capacitor, and they are in parallel. And by the very simple formula, we know that their equivalent impedance will be, which will be given by this formula, that 1 by Z will be equal to this 1 by R plus iota omega L plus 1 by iota omega C. So if you solve this term, directly you get this term. Now here you take the LCM of this as iota omega C. If you take the LCM, then these terms will be there. Then this denominator, after taking LCM, and this denominator will be cut, and you are left with this. Then we will take this approximation that R is less than iota omega L, because R is what? It is the resistance involved in this inductor. So obviously the dominating part is the inductor only. So from here we can ignore this R. Moreover, for this omega square we will put 1 by LC.